Hi everyone, this is lesson 5 of solar energy application course, and we are still in the solar radiation definitions as discussed before. This is the main textbook, and there are some other ones which will be introduced during the course. In the previous session, we discussed about some important angles in solar calculations. The sun path diagramming was introduced. A short discussion we had on solar tracker and shading. Today we want to complete the definitions with adding some more new definitions and a discussion about the extraterrestrial radiation to open the road for further discussion in the next weeks. If you remember, a solar constant was the energy from the sun per unit time received on a unit area, where the area is perpendicular to the sun rays at mean sun-earth distance and outside the atmosphere. And as you can see, there are 5 conditions for GSC. Let's review. Per unit time, so the unit is watt or joule per second, received on a unit area, so the unit will be watt per square meter or any other appropriate area unit. The area is perpendicular to the sun rays, so we are discussing about a surface which is normal to the sun rays. So GSC is on a surface which is always normal to the sun rays. And at mean sun-earth distance, because you may remember that the earth-sun distance is not constant during the year, but if you take an average value, then the value of solar radiation on this average sun-earth distance will be named solar constant. And outside the atmosphere, so the value is not on the earth, but it is outside the atmosphere, or you can see here on the earth neglecting effect of atmosphere, because I explained before that the distance, the thickness of the atmosphere is not really a large value comparing with the distance between the sun and the earth. Okay, so radiation outside the atmosphere or neglecting the effect of atmosphere is called extraterrestrial radiation. This is the definition of solar constant, which is 1367 watt per square meter at mean sun-earth distance on a surface which is normal to the sun, placed outside the atmosphere or neglecting the effect of atmosphere. But there are some modifications needed. The modification 1 is the inverse square law. You may remember that the distance between sun and earth is not constant. It varies during the year, and according to the inverse square law, the intensity of light is inversely proportional to the square of distance. So the value of solar constant actually is not constant during the year. So at first you should correct for the distance variation. So if solar constant is modified for its variation throughout the year, you can see that you should multiply it by a parenthesis shown here. This is the modification to include the effect of sun-earth distance variation, and the result is named GON. So whenever you see GON, it is solar constant modified for the distance between the sun and the earth. The N in this formula can be found either manually or from this table. For example, if it is, for example, 20th of May, then the day number is 140, adding 20 to 120. The graph here shows the result, and as you can see, during different months of the year, the value of GON, which is here, will vary between maybe 1412 and to a minimum of around maybe 1321 or 2. And so this is the average value. Modification 2 is that GSC is on a surface which is normal to the sun rays, but generally we need solar radiation on a horizontal surface. So the next modification will be how to calculate the solar radiation on horizontal surface like the one you can see here. In order to calculate the solar radiation or solar constant value modified for the radiation on a horizontal surface, you should multiply it by cosine of theta z. And if you remember, theta z is the zenith angle, where zenith is normal to the surface, or as we name it, khatt al-ras, and so this angle will be zawiya khatt al-ras. So if you multiply the previous equation by cosine of theta z, where cosine of theta z is defined before in equation 165, you can calculate the solar radiation on a horizontal surface. Let's have a short review of what we said. First, we told that we have a constant named solar constant, which is energy from the sun per unit time on a unit area perpendicular to the sun rays at mean sun Earth distance outside the atmosphere. The value is 1367 watt per square meter. Next, we modified it for the variation, or corrected it for the distance variation between the sun and the earth, and the value will be this equation as shown here, and the name is GON. And finally, we calculated the value on a horizontal surface, okay, and corrected. This is certainly corrected for the distance because you have the parenthesis here, and this will be the value of solar radiation outside the atmosphere. Let's have a review on this. This is energy from the sun per unit time, so it's power on a unit area, so the unit will be watt per square meter still, which is on a surface which is horizontal, and corrected for the distance variation by this parenthesis outside the atmosphere still. Okay, so this is the extraterrestrial radiation. Let's do some math now on this equation. This is the extraterrestrial irradiance on a horizontal surface G0, okay? And if you substitute the value of cosine of theta z here, then you will have this equation 110.2, by which you can calculate at any day of the year, at any location which is defined by phi, and at any time of the day which is defined by omega, what you can calculate the solar radiation or irradiance actually outside the atmosphere, which is extraterrestrial, on a horizontal surface. But please note that it is the extraterrestrial irradiance, okay? Just I want to remind you that we had two parameters. The first was irradiation and then irradiance. Irradiance, as you may remember, is the instantaneous value of solar radiation at each time moment, okay? This is the irradiance. The unit is watt per square meter. But the problem is that generally, well, this is important also, but the more important one is irradiation. Generally, we need to calculate the daily energy received from the sun, which is named irradiation or insolation. I just want to emphasize that you should very carefully know the difference between these two, because this is the instantaneous value, it's a power, and if you integrate the area below the curve, you will be given irradiation or insolation, which is not power, it is energy, because it's multiplied by time. It's the integral of G0 dt from sunrise to the sunset. Now, if you want to calculate the irradiation from the irradiance, there are some methods which I summarized below or here. These are the methods to calculate the extraterrestrial irradiation or energy on a horizontal surface. The first, and maybe the best, is the integration of irradiance from sunrise to sunset. So you can integrate the previous equation from sunrise to sunset and calculate the irradiance on that day. The next is a figure in your book, figure 110.1, as you can see on the right. And the third or next final is table 110.1 in your book. There is a table, as you can see here in the right bottom here. And by this table you can also calculate H0. I just want to remember that H0 is the irradiation extraterrestrial on a horizontal surface. So let's go through these three methods. Method 1, integration of irradiance from sunrise to sunset. You have the equation for the irradiance here, G0, which is watt per square meter. And if you integrate the equation from sunrise to sunset, this will be the result, which will be shown by H0. So by H0, we mean the extraterrestrial irradiation on a horizontal surface, okay? Daily. This is the daily value. How you can distinguish between days? By n, as you can see here. So for each day, you should put the value of n for that day. Omega s here in this equation is the sunrise or sunset time or hour angle. The value of n, as told before, may be found from the table 161 in your book. Or you may also use the n for the average day of the month. Also, it's possible. Then you will calculate the H0 for the monthly average daily value, monthly average daily value for that month. You have a homework here, as you can see. The homework is to drive equation 110.3 by integrating 110.2. You may remember that this at the top is 110.2. You should integrate this equation to reach to equation 110.3, which is shown at below. Okay, as before, there are some rules which you should obey actually, and write the full name at the top of all answer sheets. Write the text of the question, for example this in the answer sheet, the subject of the email, combine the file into one PDF file. For other details regarding the deadline for sending the homework to me, please refer to the Telegram channel. Okay, let's go to method 2. If you remember, we had three methods to calculate H0. Method 2 is using equation figure 110.1 in your textbook. In your textbook there is a picture, as you can see here. This is the latitude. There's a similar picture for the southern latitude also, but we are in the northern latitude and northern hemisphere, so we use this figure. Here is the latitude. For example, this is 30, 40, or any other one. Go to the appropriate day number, or maybe interpolate between them, and then to the left you can calculate or see the value of H0. As an example, find the extraterrestrial irradiation on horizontal surface in Basra, Iraq at a latitude of 30.5 n on 10th of December. So you may find 30 here as an approximation, because it may not be possible to find 0.5 in this picture or figure. Go up, cross with the 10th of December. Okay, this is 10th of December, and then to the right you can see that the value is maybe approximately 20 or somewhat less. What's the unit? Megajoule per square meter. This is daily, or megajoule per square meter per day. So the meaning is that in Basra, in Iraq, for the month of December, approximately, or more exactly on 10th of December, the daily energy received on a horizontal surface, please note, neglecting the effect of atmosphere, because this is the extraterrestrial radiation, is 20 megajoule per square meter. The next method, or third, is using table 110.1. There's a table in your textbook. You have here the latitudes and here the months. Then by crossing you can find the value of monthly average daily extraterrestrial radiation. Let's have the same example. Find the extraterrestrial radiation on a horizontal surface in Basra, Iraq at this latitude and this date. Okay, you can find 30 here, December here, so you have the value of 19.9. Please, once more, pay attention to this definition. This is the monthly average daily extraterrestrial radiation. Please note that this is not for all the sun. This is not the summation for all days in December. This is for just one day in December. This is the monthly average daily. This is important, okay? This is daily extraterrestrial. But this means that it is averaged for the month of, for example, December. So if you want to have a simple calculation, you can use this table. I think it is better. You can use either this table, okay, for a rough estimation, or you may refer to the equation here if you want to put the value of exactly each day in the equation. They are possible. Both are possible. So I recommend either using this table for rough estimation or using this equation if you want to draw more exact value. Okay. If you want to calculate the extraterrestrial irradiation on a horizontal surface, not from sunrise to sunset, but from time omega 1 to omega 2, for example, from 10 o'clock in the morning to 2 o'clock in the afternoon, then it is also possible. Just you should correct the limits of integration. Instead of using sunrise to sunset as the limits of integration, you may use different times, for example. Please note that the times should be first they should be solar time, and the next these should be converted to hour angle. We discussed how to convert the time from local time to solar time and from solar time to hour angle. So please note that omega 1 and omega 2 in this equation are hour angle, okay? And the name is I0. So I0 is the extraterrestrial irradiation on a horizontal surface, not from sunrise to sunset, but from between two specified times. One more definition remained in chapter 1 is air mass. It is also an important parameter. Air mass, which is defined, actually we missed to discuss about this, and I put it here at the end of chapter 1. Air mass, which is shown by M in this book or in this course, is the ratio of the mass of atmosphere through which beam radiation passes to the mass it would pass through if the sun were at the zenith. So this is a ratio, first of all, okay? This is not mass, because when there is a ratio but between the ratio of two similar parameters, then there will be no unit actually here. So the first is that it is a ratio, the mass of atmosphere through which beam radiation passes to the mass it would pass through if the sun were at the zenith. But actually, to simplify it, generally we take it as a ratio of two distances, the same distances. If actually the distance through which the beam radiation passes, actual path of the sun, to the ratio to the value or distance which the sun beam passes if it were at the zenith. Where is zenith? Zenith is here, your overhead. So if you look at your top of the head, this is the distance of the atmosphere, if of the minimum distance which the sun rays may pass through the atmosphere, and this is the actual path it may be at each time of the day or each day of the year it passes. If you want to calculate the value, you can use simply the equation 151, which is 1 over cosine of theta z. And you may remember that theta z or zenith angle depends on latitude of the location, it depends on the day of the year and hour of the day. So just to show you what's the meaning actually, here you can see as an example the meaning of air mass as an example for Berlin. Again, I put it here in a maybe simpler form. The air mass is the path length which light takes through the atmosphere. For example, this path you can see here, this light color is atmosphere and this is the outer space, okay? This, for example, is the actual path which the sun has on March 2nd on October 12th in Berlin, okay? Normalize to the shortest possible path length. What is the shortest possible path length? This is the shortest possible path length. So the ratio between this and this distance is called air mass. So air mass 1 will be at this position when the angle is 90 or 90, and at any other position, okay, the air mass will be bigger than 1 because this is the least value. What is the importance of air mass? Actually, it has many applications, but one of the most important ones is when you refer to the data sheets of the solar panels or modules, for example. We'll discuss about this later, but just a short review. This is a data sheet for a solar module, and you can see that these are the electrical performance of this module. For example, power, open circuit voltage, short circuit current, and other. But the important point here is that whenever a solar module is tested, the test conditions are not are actually standard test conditions. So it's not possible, for example, for any manufacturer to test his or her panel at desired, for example, condition. There is a standard test condition, or STC. And as you can see here at the bottom, a standard test condition is when the irradiance is 1000 watts per square meter. You can see that the meaning of these terms in the data sheets. Maybe you have seen them before also, but you know that, for example, irradiance is different with irradiation. Okay, by the way, STC is an irradiance of 1000 watts per square meter when the module temperature is 25 degrees C and air mass is 1.5. So you can see that air mass is one of the conditions in the standard test. So the meaning is that, for example, this special solar module which has a Pmax, or maximum power of 170 watt, will give you this 170 watt only if you have this radiation, this module temperature, and this air mass. So if any of them varies, then the value of 170 will also vary, and this is very, very important. We will come back to it later. Okay, now what's next? Up to now, we learned how to find the extraterrestrial irradiance or irradiation on a horizontal surface at any location. You can do this, okay? For example, if I ask you to calculate the extraterrestrial irradiance at this location on this time or date, you can calculate it. The same can be done for the irradiation. In the next lessons, we see how to calculate terrestrial. Please compare these two: terrestrial or real irradiance or irradiation on a horizontal surface again, and then terrestrial irradiance or irradiation on a tilted surface at any orientation. So this will be the target for, or maybe 2-3 next sessions. Okay, thank you. This is end of lesson 5. We had a short lesson today, and thank you for being with me. Take care and bye.